So, all right, we're going to talk about dissolving a solid ionic compounds for ionic compounds in water. Okay, so how soluble, it doesn't have to be ionic compounds, I guess, just dissolving a solid in water. We can talk about it being infinitely soluble, and infinitely soluble just means you could basically keep putting more and more solid and it would keep dissolving. Now, when we talked about dissolving solids, we talked about undersaturated, saturated, and supersaturated solutions, okay? We could say something is not infinitely soluble, but it's very soluble, highly soluble. We could say soluble. These are all degrees of solubility. If we say something's insoluble, here's the catch. It doesn't mean that none of it dissolves. In fact, the body of part 5 is talking about insoluble salts. So it just means that it's very, very resistant. Yes. So these are some general, for ionic compounds, general rules that you want to kind of know, have in the back of your mind or know. For ionic compounds, if the cation is a 1A, the top 1A's, so lithium, sodium, potassium, then it'll generally be soluble. If it's an ammonium, it'll be soluble. Exceptions, though, there are some exceptions. If the cation is a polyatomic cation, if it's nitrate, what is that, chlorate and perchlorate, that last one, the CHU one, is actually acetic acid, acetate. If it's acetate, then, or those other ones, it's generally soluble, the salt is soluble. If it's a monoatomic anion, if it's a halide, the 7A elements, the top ones anyway, chlorine, bromine, and iodine, then those salts are soluble unless the cation is silver, mercury 1 polyatomic cation, or lead 2. And then they're insoluble, those halides. So. Sulfates are generally soluble unless your cation is calcium, strontium, barium, or lead 2, and then the thing is generally insoluble. Salts of these these down here are insoluble. So generally your carbonates, phosphates, this is oxalate. Of course, this is chromate, sulfide, hydroxide, or oxide. If those are your anions, then it's generally insoluble, unless your cation is pretty common, sodium, potassium, lithium, or, again, ammonium. Kind of refer to our first slide. So, I don't know what to tell you about kind of getting those under your belt, but you probably want to. So we're going to switch gears to things that are insoluble, and I just kind of want to remind you, for instance, if we take something that's insoluble, here's our beaker. We're going to make it an aqueous solution, so there's my water, and I'm going to dump in, I'll call it I'll call it AB, where A is the cation and B is the anion, ABS, solid. Then we could talk about this dissolving process, and we could say that AB, my ionic compound solid, will dissolve in water. That's going from left to right to form A plus AQ and B minus, AQ. Make sense? But let's just say that there's a sludge down here. This is my solid stuff, okay? Remember we talked about dissolving that. Remember I said that some of it will dissolve and some of it will precipitate out. And we said when the rate of dissolving equals the rate of precipitation, your system is at equilibrium. Ring bells? So that's kind of the scenario that we have. It's definitely not infinitely soluble because we got the sludge down there. So it's basically what we would say, it is insoluble. Definitely not. It's not. Definitely not. You know, definitely soluble. Okay. Well, here we go. So this is the kind of scenario I set up, where now it's kind of fun. These little You probably recognize these as subscripts. These are how many cations you need. These are how many anions you need. Of course, when you show the dissolving process, you get those subscripts end up being stoichiometric coefficients. Now, these a system in equilibrium, there's all sorts of applications. And I mentioned that actually Unit 4 in here is all about pHs. Hydrogen and hydroxide ion concentration of aqueous systems is just one big chemical equilibrium. So I mentioned that because now we have a chemical equilibrium. And remember, we said the rules are if you have something that's in its solid state, okay, that will not appear in your equilibrium constant expression. Now, it's a small thing, and not really a small thing, but instead of a C down here, we're putting SP because it's a special equilibrium. It's an equilibrium of an insoluble salt. Okay, but otherwise, it's kind of all basically the same. Sometimes I call this a KSP expression. Okay, so what is KSP? KSP is the constant for that equilibrium, and it's called the solubility product constant. Solubility product constant. And I guess it kind of makes sense because in the in the KSP expression or in the equilibrium constant expression, we're just basically multiplying or taking the product of the ion concentrations raised to their stoichiometric coefficients. Okay, so that's your KSP expression, insoluble salt, solubility product constant. So we are going to revisit the idea of solubility. Remember we talked about, like, let's see, what was it? Like, how many grams of this salt can dissolve in 100 grams of water, that sort of thing. So we'll look again at solubility, but don't confuse solubility with KSP. Okay, KSP is the constant associated with that equilibrium. All right, so let's take a look at how this works. So here we have silver chloride. So that was what that was your last little equilibrium that we did in Thursday's lab. Silver chloride is insoluble, but we can say it's just dissolves like this to just a small amount, and it's related to how much dissolves is related to the solubility product constant, like this. So that's your KSP expression. So you're going to want to, in fact, you're going to have some practice at this. You want to be able to write the KSP expression for a salt like that. Notice that it changes up a little bit with the silver phosphate, because notice that when it ionizes or dissolves, we actually get 3 parts of Ag+. Okay, so this 3, we end up with 3 parts of that, and of course there's 1 of this. So yeah, I'm making you remember about your whole Chem 1 stuff. Okay. So we would write the expression like this. KSP then is equal to the molar concentration of the silver ion raised to the 3rd power cubed times the molar concentration of the phosphate ion. I don't know how many times I'm grading the exam that you guys are going to take a week from Thursday, and just something as simple as, you know, just blowing off, because you're concentrating on other things, the stoichiometry of the dissociation or the ionization. Because then that tells you how your expression needs to be set up. Okay. So kind of we have silver nitrate, and remember that most nitrates are soluble. So silver nitrate, and then we have sodium sodium iodide and B, minding their own business. They're both clear solutions. Those are 2 soluble salts. And we're going to talk, is it now? It's coming up, about this ion exchange reaction. Basically, you have cation, anion, and they switch partners. And the way these work is if a solid precipitate can form, it will. Sometimes I wonder, well, why don't they just not switch partners and stay soluble? But it doesn't work that way. Okay, so anyway, when you mix the 2, this is what you get. Isn't that pretty? That's kind of what you guys saw Thursday's lab. So your choices for things to be soluble, this is, kind of think along these lines, of course, would be you know, your silver is going to connect up with your iodide, and actually that's what's insoluble. And your nitrate is going to go with your sodium. Sodium nitrate is soluble. And you're like, how would I know that? Well, I think the rules I told you a little bit ago said that halogens like chlorine, bromine, and iodine are soluble unless they combine with certain cations, and silver was one of them. So this is AgIs. After an exchange reaction. Okay, so here we have all sorts of tables, I think. So do you guys buy this that, let's see, how do I say this? So we said we said salt AB breaks apart to form A plus B minus. And you can write the KSP expression is equal to, let's just assume these are all coefficients of 1, molar concentration of A plus times raise the first power times molar concentration of B minus, also raise the first power. My point was going to be, we said that if your KSB values are small, does this make sense? That actually, if it's very small, you don't have very much products. So the smaller it is, the less it dissolves. Okay, so the first one, 1.3 times 10 negative 33rd, that means that it basically stays in its unionized form, in its non-dissolved form. You know, and if we pick on like magnesium carbonate there, you know, that's a factor of many factors of 10 larger, which means it definitely favors the product side more than the 1 times 10 to the negative 33rd. Okay. So this is a good reference. Okay. So let's work a problem. Let's see, what was I going to do? So here is basically we're dealing with lead 2 chloride, insoluble salt, and PbCl2. You can see this on the next page. What I would suggest is when you're faced with these in homework or in a test, right away, even though it doesn't say it, you don't have to draw a picture, but I definitely would draw the equilibrium because you just need to. Okay, so we had the lead plus 2 cation, AQ, plus 2 chloride ions, AQ. If nothing else, it makes you feel like, oh, I know what's going on here. We can write the KSP expression, equilibrium constant expression. It'd be the molar concentration of Pb plus 2 raised to the first power times the molar concentration of the chloride ion squared. Okay, and of course we don't have a value for KSP here. But it said that I can dissolve a maximum amount of 0.0162 moles per liter of this will dissolve. So do you guys buy this, that the way this breaks apart, that I could go ahead and I could write 0.0162 molar here? What would I write here? What's the molar concentration of chloride ion? Times 2. 0.0324 moles per liter. That makes sense? Well, then we're almost done. Calculate KSP. Do you see why I think you had to draw this? So calculate KSP. So these are at saturation. So these are at saturation, at equilibrium. So these actually are the equilibrium concentrations. So I'm almost done. What you're going to see me do next is take this, put it in there, take this, put it in here. Now, again, I'll take my red pen and I will circle. We just get excited about getting the answer right and we forget about the stoichiometry. See where all that came from? It's really, really easy to do, but we're almost done. here in a minute, we're going to do ice charts. I don't really need to do ice chart for this one, I don't think. So when we substitute 0.0162 moles per liter in for the lead molar concentration of 0.0342 and square it in for the chloride ion concentration, it looks like this. And remember, we're all about units and factor label process, but the units for our equilibrium constant expressions all cancel out. So rounded to 3 significant figures, we have 1.70 times 10 to the negative fifth. Now these are temperature dependent. I think my notes said that a little bit ago. And I think anytime you look up a KSP on a table, it's usually at 25 degrees Celsius, which is standard thermodynamic conditions. Okay, all right. So let's see, we're gonna, we won't do this, get this whole part, but I want to get to the next assignment slide if we can. So let's take a quick look at these. They look like we're in chapter 18. Okay, looks like this. So what I did in my notes was actually do the first one for you. Write the KSP expression from these equilibria. That one should do fine for you. The next one I did the first one too. Let's see. Oh, in this case, you're given the KSP expression, the equilibrium constant expression of the insoluble salt, and you need to backtrack from that to the chemical equilibrium. It's going to bring back memories of ionic compounds. And then the last one looks like this, where I think I'm wanting you to do two things. Notice you're just given a KSP value for a salt in parentheses, and go ahead from that, unpack the equilibrium, and then write the KSP expression for both of them. Nothing to do with your calculators, though. Nothing to do with your calculators yet. All right. So KSP, solubility product constants. Sometimes I can't. KSP, solubility product constants. They are related to solubilities. The product constants are related to solubilities, but not directly, and we'll kind of take a look at that here in a minute. We can use KSP values to anticipate if there's an exchange possibility, exchange reaction like we looked at before. We can use the KSP values for the different possible salts to know what's going to precipitate first. Those are fun. I'm just warning you, they're fun. I think we'll get to those, I think on Wednesday. Yeah, these two are kind of related to each other. Okay. So, like I said, 25 degrees Celsius is usually the temperature at which those KSP values have been given, and it's totally like we've talked about before. If solubility changes, then KSP values will change too. So it's very much temperature dependent. So I have a bunch of handful of tables to show you. Hopefully, if you need the values, you have your textbook handy, because I think they're hard to read in your notes, aren't they? But I'm hoping we all have a sense of, you see that one raised to the negative 44th power? What is that? Cobalt-free hydroxide? That's, and again, we're not really comparing apples to apples directly, but that low KSP value means it's just not very soluble. Okay, the lower the KSP value, the lower the solubility in general. Next one, next one. Okay. So, let's do another one. Okay, same thing. x equals 5.3 times 10 to the negative fifth. Now, by definition then, the units on molar solubility would be moles per liter. Okay, so let's work a problem. I think I might have a couple problems. Can't remember. Okay, so I wonder if I want to do, I'll just copy it. So we have, you know what I'm going to do, so go ahead and feel free to work ahead if you want. The silver chromate. So we're going to go ahead and write its equilibrium. So Ag2CrO4 in its solid state is in equilibrium with its dissolved or ionized form. We have 2 moles of Ag plus and 1 mole of CrO4, 2 minus. We'll include those little AQs so we know they end up in the KSP expression. So KSP is equal to the molar concentration of the silver ion squared, right? And also then times the molar concentration of the chromate ion raised to the first power. And the value was given as 1.1 times 10 to the negative 12th. Cool. So if we're doing an ice table, initial change at equilibrium, the only 2 things we need to worry about are the things that show up in your expression. So we'll have a column, the molar concentration of the silver ion, and we'll have a column, the molar concentration of the chromate ion. So again, I would encourage you to work this sort of problem. Like I said, the common ion effect, when we work these Wednesday, we're going to see that it already has some ion in there. But now we're going to say the initial is 0. We're going to make the change plus x, because we are going to take x as the molar solubility. It's, ooh, wait a minute. Almost caught myself. Let's think through this. We're going to make x the molar solubility. How many x's of silver ion are we going to get? Yes. And how about chromate?
1.
Yes. So that's why on an ice chart it ends up with a silver, we get 2x, and with the chromate we get simply x. So initial, apply the change. We have 2x for the silver at equilibrium. We have x, okay, for the chromate. Now we have to take these quantities and plug them back in to our expression. So we have KSP is equal to the silver squared, quantity 2x squared, times the molar concentration of the chromate, which is simply x, which is equal to 1.1 times 10 to the negative 12. Now, don't forget we have to distribute the square through. Okay, so I usually rewrite this as 4x squared times x. And then I gather my x's together, 4x cubed. Okay, so this actually then talks you through totally that sort of thing. If we let x be the molar solubility of the silver chromate, then at equilibrium, the molar concentration of the silver ion is 2x, and the molar concentration of the chromate ion is x. But I'm telling you, I almost messed up over here. If I didn't have the KSP expression, if I didn't have KSP is equal to the molar concentration of Ag plus squared times the molar concentration of the chromate, I probably wouldn't get the right answer. So when we substitute in there, we need to we're not done yet. So what I would do is divide both sides by 4, and that gets your x by itself. So this is actually dividing both sides by 4. I would do it stepwise, not like this. Divide it by 4, that's your KSP, and then you need to undo the cube. So we're going to find what we call the cube root, which might be kind of new to some of you. Cube root. okay? So actually on your calculator, you can take it caret raised to the quantity 1 divided by 3 n quantity. Round it to two significant figures, we end up with 6.5 times 10 to the negative fifth moles per liter. That's the molar solubility of silver chromate given that KSP. And if you're kind of thinking there's a pattern to going from KSP values to molar solubilities, you are right. There's definitely a pattern. But I would just encourage you on your homework and on your exam, write down every step that you put into your calculator. Because even if you randomly come up with, and I've seen it happen, it's almost like taking a jump. Oh my gosh, what game was I watching where the dude, was it you and I, who like beyond half court made it in. What game was that? It's the tournament. But anyway, it's crazy. I think it was you. But anyway, even if you get the right answer and you don't show me how you do it, I'm not working. Okay. So here's where I kind of want to put in context a little bit how the solubility product constants, those KSPs that describe the equilibrium, how those kind of relate to something we're already familiar with, just generally solubility. So this is a good example. Here we have calcium carbonate and silver chromate. Now just by, I told you the smaller the KSP, the lower the solubility. So just upon KSPs, you'd be like, oh my gosh, silver chromate must be less soluble than calcium carbonate, but that's not the case. That last column there shows you the relative solubilities, their molar solubilities. And as it turns out, it's not much because they're both the magnitude 10 to the raised negative fifth, but actually the silver chromate is just a little more soluble, not much. Okay, and if we just did this, we would think it was less soluble. And here's the deal, and it's basically, if we look at, how if we go A is the cation, B is the anion, it falls into a pattern. In this case, we have an AB, one formula unit of each, and here we have an A2B. A2B. And the fact that they don't have the same pattern means you cannot compare KSPs directly. These, what's that? I can.
And can you say that one more time, please?
Yeah. If they, so if you look at kind of the cation anion pattern, so here we have just AB because we have one calcium and one carbonate, and here we have A2B where we have two silvers and one chromate. So if they were the same pattern, then you could compare these directly, but they're not the same pattern. Yep. Yep. And so actually the next slide reinforces that, because here we have these are all the same pattern. They're all A1, B1. And here's the KSP values. And so let's see, we said the lower the KSP, the less soluble it is. Okay? And actually, in this case, it is true, because these are all the same pattern. But I feel okay about it, because a few slides ago when it was like 10 to the negative 33rd, I'm like, dude, that was so way out there. That's insoluble. Or, 10 to the negative 5th, I'm like, a little bit soluble. Because that's kind of a high KSP for kind of a high KSP. Okay. So yeah, there's definitely a formula, and I think your textbook probably talks about it, and feel free to use it. In fact, I'm going to kind of use it on your homework. But this, if I'm doing a test, this is what I go back to. Okay. So for instance, if you had the KSP value and you wanted molar solubility, just like we did on this one, and if the pattern is one cation, one anion, okay, you can knock out molar solubility, let molar solubility be equal to X, and X squared is equal to KSP. That's it. Okay? But I would do this on a test. Okay? Now, if you have one cation and two anions, okay, you kind of take it through the thought process. you end up, that's what your KSP expression would look like. And you substitute in X for your cation and 2X for your anion. But don't forget, the anion also needs to be squared. You end up with, does that look familiar over here? Yeah. So, and it's, I thought that would work. Look, so this is 1 cation, 2 anions. This is 2 cations, 1 anion. It's the same diff. Isn't that wonderful? I love math sometimes. Okay. So if you work through it and knock out X, that is the molar solubility of your salt, given whatever the KSP value is, etc. Okay, so let's take a look at these right quick. Chapter 18. Okay, so I went ahead and did the first one for you. Calculate the solubility, the molar solubility. And that's another thing. It's a subtle thing, but hopefully if somebody tells you molar solubility, that's the moles per liter. Molar solubility, moles per liter, given these KSP values. So if you want to, I've had students turn these in and not go through all this, and that's fine, but you have to, everything you put in your calculator, you have to write down. Oops, come back here. We're going to do that on Wednesday. There we go. There's only one more. Okay, the next one looks like this. Oh, okay. Okay, the next one says, now I've seen this one done different ways too. I wrote this hints up like a year ago. But basically we have, 5 salts, and you're supposed to say how are they, arrange them according to molar solubilities. Remember, KSP is not molar solubilities. And we're definitely kind of a little bit over the board, not too bad. So there might be different ways. Notice that we only have 1 A, 2 B, the last one. Otherwise, we're just A, B's, aren't we? So, but what I told students a year ago was to basically come out with, convert from the KSPs to molar solubilities and then arrange them. So I know that seems like a lot of work. So you guys can be creative on this if you want to. If you guys, but you can't just guess. It has to be something that you think that me, where I'm at, can follow your logic as to how you work.
Out in a silver to sulfate, even though we can't compare it.
Oh, no, you can't. See, if you do the red check marks are compared directly. It's the KSPs you can't, but if you get molar solubilities, you're totally there. Yeah. So that's, but it's, I know it seems a little labor intensive. It seems like there should be a way not to have to do all of them, because the first 4 are the pattern AB, and the KSPs you can look at directly and know where they're suited. So if you can kind of insert the last one, silver nitrate, silver sulfate somewhere. So, okay, does that make sense? Okay. So I'll just kind of let you do it. Okay? Well, that's a good place to stop.